So good afternoon, good morning, good evening. So we have the pleasure here to have today Professor Rajesh Gupta from UC San Diego to talk about programming human spaces. But before doing a short introduction of his CV, I'd just like to announce some next events. So next week, we are going to have a talk by Rodrigo Calderon Rico from Apple, Cupertino, USA. So he's going to talk about missing hardware functions to apply intelligence in communication systems. If you address also this YouTube channel where you are now, you can see also all the recorded versions of talks from last year. So it's more than 24 recorded sessions related to the Friday's CASS talks with very nice talks. Then we have also a set of industrial talks. And the industrial talks, we have people from working in companies that are doing microelectronic work in Latin America. So you have companies from Costa Rica, Argentina, Brazil, Chile, and so on. So this is a set of 20 talks available there. You can also see the talks that were recorded during the CASS Rio Grande do Sul workshop last year. So you can see here some very nice names of speakers. And then also there is the talks related to the digital processing of visual signals and applications workshop from last year. There is also the talks some of the talks related to the microelectronics school last year. So you can see here the speakers from France, Taiwan, Chile, Colombia, and USA. And so the next edition of the South Microelectronics School 2021 and the South Symposium Microelectronics will be end of April. So the call for papers for the symposium is open, and soon you are going to have the announcement of the program of the school. So don't lose this opportunity. Then end of July, we should have the first edition of the seasonal school on monolithic 3D circuits. By the way, this photo here is of a museum in Porto Alegre. The architect was Álvaro Siza from Portugal, a very nice one. That's really a 3D building. And it's already agreed that the second, third, and fourth edition of this seasonal school will be in France, Singapore, and China. Then the fourth edition of the seasonal school on physical design automation is scheduled to begin of August from Florianópolis, Brazil. So as you should know, first one was at Porto Alegre, 2017, TI in Taiwan, and 2019 it was in Beijing, China. Also, the International School on Effects of Radiation on Embedded Systems for Space Application that is being organized around the world, so each year in a new country. So this year we hope to have a face-to-face edition in the wine region in the south of Brazil, so near Porto Alegre. So soon also we are going to publicize the set of speakers, and it's also being prepared a book based on the slides to be published in the series of books by IEEE Sequencing Systems Society. Also, I'd like to use this opportunity here to invite all you to be active in Sequencing Systems Society activities, and to propose any activity in the society. First point, you must be a member of a CASS chapter or a CASS student branch, and you can propose anything that you have in mind to the CASS chapter or to the CASS student branch. And CASS has several calls with funds to support activities. One is the student design competition with nice grants to winners. The second is the CASS outreach calls, so you can have an idea of any activity you can propose to these calls. Seasonal schools, So the next deadline to propose 60 seasonal schools is May 31. The pre-doctoral grants for students that are doing PhD, they can spend 2-3 weeks abroad. So the deadline is next Monday, March 1st. The student chapter grants, so there is a call that will be announced soon with grants for chapters, student chapters to organize activities. There is also the student travel awards to attend the CASS conference around the world. So now, as we have the COVID problem, you can also only request support for your registration fee. So the deadline is also next Monday. Also, paper awards, also deadline next Monday. Chapter of the Year awards, deadline also next Monday. And several other society awards that you can see in the CASS webpage. And there is also the CASS Distinguished Lecture Program with very nice speakers. You can see the list in the CASS webpage. And you can also nominate names for the next team of Distinguished Lecturer of the Society. So this is just a brief of a set of opportunities that you have to be active in the society and also to have the support of society to organize activities. And for students and graduate student members, there is a nice promotion by IEEE, 50% discount for this membership. So for the ones that are becoming new members, but also for the ones that are already members. So you just have to use the code future50 when doing your payment of your membership. And but we don't know till when this promotion will be available. So it's better to use it as soon as possible. So so today we have here Professor Rajesh Gupta that kindly accept our invitation to give this talk. And Professor Rajesh Gupta serves as a founding director of the Harisilguru Data Science Institute and as a professor of computer science and engineering at UC San Diego. Professor Gupta's research is in embedded and cyber physical systems with a focus on sensor data organization and its use in optimization and analytics. He currently leads the NSF project Metro Insight and co-PI on DARPA SRC Center on Computing on Networking Infrastructure with the goal to build a new generation of distributed cyber physical systems that use city-scale sensing data for improved service and autonomy. He currently serves as editor-in-chief of the IEEE Transaction Computer-Aided Design of Integrated Sequencing System. He was also former editor-in-chief of IEEE Design and Test magazine. So Professor Gupta holds the Qualcomm Endowed Chair in Embedded Microsystems at UC San Diego and the INRIA International Chair at the French International Research Institute in Rennes, France, and the Bretagne, so nice location to go also. And he is a fellow of IEEE. He has the ACM and the American Association for Advancement of Science. And he has a large set of published papers, so a large set of achievements, but we are not going to show all the details because it would take too much time. So we are here today mainly to attend the talk by Professor Rajesh, that I'm sure will be a very nice one as always. So thank you very much, Professor Rajesh Gupta, and the floor is with you to start your talk.
Thank you, Ricardo. I am honored to be here. The set of YouTube videos that you pointed to just looks impressive. And this being Friday, I intend to spend weekend going through them and see. It looks like you have really collected a nice community together. Good morning and good afternoon to everyone. Today, what I'm going to do is talk about programming a new programming platform and how that is emerging. What are the challenges and what are the opportunities there? Now, any talk today, any conversation today, cannot begin without first talking about what is in front of us for all of us and the reason we are online. So let's talk about that a little bit, about the pandemic. Uh, uh, and uh, and then take it to the talk itself. Um, we know that this pandemic is spreads by breathing other people's breath, by taking in air that somebody else has breathed in, and usually that is measured in terms of viral load that one takes in the vicinity of somebody else, which is why we've asked people to maintain distance. We don't want to be in crowded gathering indoors. So there are a number of models that are developed that try to estimate the amount of infection risk one could incur in the company of a group or people, and the mechanisms are now beginning to be understood. There is, of course, direct mechanism of droplets being inhaled. There's also aerosolized particles which sort of float in the air for minutes to hours, and that are inhaled. And this airborne inhalation has emerged to be the biggest source of spread of the virus. And this airborne inhalation happens through air handling systems. It happens through, exposure to toilets and so on. So there are a number of models that are built, and they all built upon models by Wells Riley and Rudnick Milton that sort of try to estimate risk. And rather than using the formula and symbols, essentially the formula basically is that the risk is equal to 1 minus e raised power minus bad things over good things. In other words, if you don't do any bad thing, your risk is 0. For example, you're isolated in a remote place without any exposure to any infectors. On the other hand, if you're in a society or in a workplace, you're going to be exposed to infectors. That's a bad thing. You're going to be spending time with them. The longer you spend, the more exposure. That's a bad thing. Somebody talking loudly or singing will give you more infection than somebody not talking. Now, in those list of bad things, as they increase, your risk it rises pretty rapidly. This is exponential curve, so the slope is high and then it sort of decreases, and it sort of goes up. And so if you're trying to reduce the risk by doing good things, then you are sort of traversing this curve downwards. Now, one of the good things in this area is really the amount of fresh airflow around you. Now, that airflow is measured as cubic feet per minute in terms of velocity of air moving around you. And at a gross level, at the level of a room or a building, it is measured as number of air changes per hour. It really is a constant, time constant. And so a air change per hour of, let's say, 5 simply means that the time constant of a change in pollutant in a room is 12 minutes. So in 12 minutes, it drops by 63% or exponential power 1. All right, so that is so there have been number of guidance from standards bodies that tell us what the airflow should be. For example, ASHRAE, which is in North American standard, has come back with recommendation that normally designed building for ACH 2 or 3 should be increased to ACH 6, for example, and they should use filters of certain kind and try to maintain an airflow per person of 15 cubic feet per minute. In case of hospitals, there's a much more strict standard. For example, maintaining air handling air change to be 12 per hour, 12 changes per hour. The European standard REWA has many different measures to reduce risk, but again, it comes to the the flow rate of 21.8, which is basically the translation from metric to imperial units. And of course, we often look into estimating the amount of fresh air by estimating the amount of carbon dioxide in a space. So oftentimes people would monitor just the amount of carbon dioxide as a proxy for how much of rebreath there is in a room. So when we look at these airflows, the number of calculators that have come up that sort of give you an estimate of your risk. For example, and this is one of the calculators online, but there are many spreadsheets and so on, that you put in the inputs, let's say air change per hour 2.3, outside airflow supply per person of 22.5, which is sort of nominal in a small room like my office. This is actually a number from my office. So 2 people in that office, and nominal is 45 CFM. And therefore, the amount of airflow supply per square feet, 0.3. Today, when we do infection control, we try to bring it to 1.2. And you have a space per person. This is additional filtration in case you have on the floor filter, and you put those numbers in. It gives you risk that your probability of getting infected is more than 50%. That's not good for a exposure for 1 hour of meeting in my office. So what can we do? Well, we have tried different numbers of airflows and so on. It turns out that if you put on a mask, if you put an airflow, if you increase the ACH in my room to 5, then your risk goes down to about 15%, and it can keep going down all the way to 5% as you increase air change per hour. So you can see there's a direct impact of how you handle the air inside to the ability to get back to work, the ability to resume normal life. We will get back to this a bit later in the talk. Let's just talk about the building itself first and why we are interested in buildings. So here's my outline for talk today. Why are we going to talk about buildings? What is so interesting about them? And what is the problem in programming human spaces? And in particular, I will address the problem of context capture, and it's used in a new programming model. I actually call it modality because I'm not sure it is a new programming model itself. With this set of tools we have built around Brick standard. And then I'll give you some examples and pointers to what future may look like, and then get back to our infection control in buildings in the context of programming buildings. So why did we get interested in buildings? It actually happened sometime in a March 2009. We had a meeting at one of the institutes we have here in San Diego. The meeting was directed by Director Larry Smart at that time, who has recently retired, and we were very worried about the global warming that was coming up. Mainly because of the increased carbon dioxide into the atmosphere, and that will lead to ice melting. There will be floods, and then there will be no water, for example. And we said, well, what can we do to mitigate this condition? And so there were a whole bunch of researchers. We got together, we talked about what is it that we can do, and we said we can make a difference, especially by focusing on 2 things. One was buildings, because they were the biggest consumer of energy, and we were spending most of our times there, and of course making the electricity grid itself very smart and green. And we said, well, that's easier said than done, but how do we start? And so, well, we said that we can start by actually turning our own facilities, the campus, into a research facility and research lab. And the concept of living laboratories was born at that time. So I was also caught up in that discussion, and we started thinking what we can do. In the next 10 years or so, we built many systems which which instrumented the energy usage inside a building. And of course, starting our own building, commercial building, we deployed these occupancy sensors first, relatively crude ones, then a bit more sophisticated ones, which are now employed in all offices in current buildings, for example. We also created remotely controllable plugs that sort of reported energy usage through wireless interfaces. They could also be shut down, they could also be throttled, and so on. And then we connected to a building management system where we could sort of monitor the energy usage. And we started looking at interesting data. For example, this is just a sampling of 5 buildings. And of course, the buildings have different sizes. So you say, okay, what is the energy usage per square feet? The first one is this black line, which is, you see the pretty flat line for a week period, August to August. So you see, we started in March, and by August, we were instrumenting and measuring data. And so this is the San Diego Supercomputer Center. This is the place where large-scale computing equipment, high-density computing equipment is. So that's one of the highest, about 11 watts per square feet, and it basically stays pretty much flat all day long and all week long. On the other hand, if you look at something like a computer science building, let's say here, blue line, you will see it starts during in the morning, it goes up during the day, then comes back down night, goes back during the day. So Monday, Tuesday, Wednesday, Thursday, Friday, then of course there's Saturday, Sunday. All right. Some people are still working, but not the others. Cal 82 is a research lab. It has many fabs, and so it has a fab and so on, which is also sort of similar to this, except that the actual energy consumption is lower of a microfabrication compared to, let's say, data center. And then, of course, the red line is the gymnasium. So your Monday, Tuesday, Wednesday, Thursday, Friday. And of course, the people who go to gym on Saturday and Sunday, in fact, only on Saturday and Sunday sometimes. So you have a decent power consumption there. And then, of course, you have residential hall, which you can barely find out because this is a residential hall in a university. So they don't really have very central handling systems and so on. And so the energy usage is not that significant. We said, well, let's take another closer look at this, and said, well, let's suppose I look at the computer science building here, this blue line. How does that look in its component? And so when you take the same data and you break it down, you actually find interesting parts here. Machine room, which is similar to a SDSC's supercomputer center, is also relatively flat. On the other hand, lighting follows this lower down curve. It's not the big component of the energy consumption. This is kilowatts. And then you have plug loads, which are networking equipment, computers, monitors. And then you have this mechanical system, which is the actual air handler that goes up. It stays up for the day and then comes back down. So this is the mechanical air handling system. Okay. So we said you can now devise measures to reduce energy consumption. So we built multiple systems. We built a system called Sleep Server that sort of made this black line become duty cycle. So if you're not in the building, if you're out there on Christmas holiday or something, the machines are still alive, but they're not consuming power. So we did that by adding secondary zones and a sleep server, which is a special piece of software, and so on we built. We also duty cycle the HVAC system. It doesn't have to be that's completely fixed. It could actually be driven by occupancy, how many people are actually in the building, if they're at all there. And then, of course, we built systems like entire duty cycling the buildings with databases and so on that sort of contain the information for the building. We also measured the data across the entire campus. So this is the energy consumption across the campus on a real-time basis. When you deployed it just on the computer science building, this autonomous system, without affecting anything else, just on a single floor, so that means you can multiply by 4 across all the floors, you had you had quite a bit of energy savings, both electrical as well as thermal energy saving. Thermal energy saving because we do also do heat exchangers inside the building. And we built a piece of software that people can carry in their cell phones to set their conditions and actually talk to the HVAC systems directly. So that was all great. Energy consumption over the years, a whole community of researchers came up in building systems. In fact, it's called ACM BuildSys. It is now in, I don't know, 6th, 7th cycle, where the researchers who work on commercial buildings and city scale infrastructures and so on get together and talk about this intersection of physical systems infrastructure with the computing folks, which is what ACM is about. And that is one example of cyber physical systems. So that was all great. But what was the problem? The problem was that all that we did worked well for one building. And when you went from one building to the other, you had to do the same thing all over again. It's like you build a computer of one kind and you have to write its code, its assembly, compiler, its operating system as you go from one computer to the other. I'm not even talking about one computer type to another computer type. So the biggest problem was that if you look at, this is the computer science building I was telling you about, all that we did was applicable and we had to keep repeating it for every building. So we ask a very simple question. Can we program these physical buildings, physical spaces, which of course depend upon their systems, not only what the state of the building is with respect to temperature and air conditions, but also occupancy. And in fact, what humans are doing, are they meeting in a conference room? Are they in their offices? Is there a new event happening? Is there an open space event happening? Whatever. So now you needed to somehow find a way of programming, or at least can create a platform. Rest of my talk is just about doing this one single goal, which is how do you create a platform out of it from buildings. So when we started doing this, we found, oh my God, this is really hard. Why is it hard? Buildings are complex. I know computer systems look very complex to people who are not in computing, but buildings is another level of nightmare. You have hundreds of dampers that each individually controls the airflow. You have many large fans. You have large pumps. You have security. You have lights. You have different conditions in different parts of the building that are exposed differently environmentally. So when you start to look at it, this complexity, you say, well, what do I do to build a system out of it? So we do what we know best. Computer scientists are good at abstracting things and creating abstractions that sort of can build upon each other, which is why we can build complex computing systems mainly because of the abstraction levels we have created. So we ask ourselves the same question. Can we create similar abstractions for not only the building structures here, but also the information flows that are happening? Now, information flow had even bigger level of complexity, where you had these thousands of sensors that sort of providing a data deluge, but you don't have that much attention. You have to somehow find a way to compress this so that you can get the attention from the operator of the building or the occupant of the building, and then whatever they give you as a feedback must be amplified into whole bunch of instructions for multiple subsystems. So this problem is not just common to buildings, but to complex systems. And in fact, this was referred to as wealth of data and poverty of attention by Herb Simon a long time ago in talking about institutional impact of computing technologies. So you have customers or users, you have a cyber physical systems in between that is interfacing with a physical system. Sometimes people use the word, the phrase digital twin or plane. So you have a physical system and you have a virtual system that is somehow causally connected to this. All right, so can we get an abstraction in place? And here is what we did. So we said, okay, here's one way to think about it. At the lowest level, you have sensors and actuators, temperature sensors, carbon dioxide sensors, switches, control parameters, PIRs, whatever you want to put there. CO2 and maybe particle monitors and so on. Then you have these sensors which are part of subsystems. For example, they're part of lighting, they're part of computing, they're part of networking, they're completely part of a HVAC system, heating, ventilation, and air conditioning, for example. They're part of security systems. So there are multi subsystems. And then on top of that, you're monitoring them on a mobile phone, you're controlling them. Maybe you have a control loop algorithm that is sort of looking at these operations of the system in real life. You're also diagnosing fault. Maybe some part of the HVAC system is not working, some lights is not working, security has failed, and so on. So you're beginning to see the picture that you can sort of layer the complexity into functional areas that you can then start to break it down and start to think about interchangeability as you would in a platform for different sensors or subsystems or applications. But one builds upon the other capabilities. And so if you did that, you would actually have a software stack for such a building. And you have at the lowest level, you have infrastructure for hardware, and at the highest level, you have the software of applications. And in between, you have services, APIs, monitoring, data storage, and longitudinal data storage, comparison from last year, and so on, and comparison from other buildings, for example. The problem, of course, is what sits in between the software and hardware. Now you know the answer to that question. In case of computing system, what sits in between is a ISA architecture. So ISA provides you instruction set architecture, provides you interface between hardware and software that sort of gives you the ability to run the same software against multiple different hardwares. And that's what we're trying to do. We're trying to create applications that sort of will move across from one building to the other. That layer is where we spent last 10 years building. And that layer, it turns out, is the most difficult part, not only technically, but also sociologically. So we'll walk you through that. And that is basically what we call a metadata layer. It's a layer of capturing the context. So while we know how to get the data from one sensor to another, the question comes up is, where is the sensor located, at what in which building, in which room? All that information is contextual information. That information is usually captured in current building management systems through metadata models. So what does metadata look like? Well, the metadata actually is different for different buildings. In fact, if you have different buildings, and you want to say a simple command, activate AC when room number 22150 is occupied. Looks simple, right? You have one sensor, you have another actuator, and you somehow need to connect it. Well, the problem is, where are the temperature sensors in that building? Do they even exist? Is it going to be estimated? But how do you set the set point? What are the temperature set point? Where are they located? So you ask that question to building management system, you get an answer from one building which gives you this metadata string. Which sort of you can make it out that it is EBU 3B is a building, this is a zone, and there is a temperature for that zone, temperature sensor for that zone. But then you go to another building, you get a different answer, a different type of a string. So this becomes a problem. So the first obvious answer is, you could be programming different computer systems with very different assemblies. You could, but then you need different assemblers. So what if we would try to create a schema that allowed us to unify this? So the real world metadata was written for humans. So you would normally never see it. Even building operators will never see it. The installers will put these things in place, and then they would program the HVAC system forever, and that is how it runs. So the only people who actually see this metadata are the ones who sort of have to do something with it at the installation of the building. And they mean different. They refer to, for example, a raw metadata could look like this, which says it's a temperature set point, the location is not given here, and it refers to an equipment of the labeled crack one, for example, and so on. And similarly, so you can have different. So there is no common parsing rules you can build. Now, we are not going to overnight change all the buildings. Buildings exist and BMS. So we need to find a way of going from raw metadata that is used today, written for humans, to one that can be used by compilers, assemblers, and programming tool chain. So how do you do this? So this is where many efforts have been done in our community, and I'm just going to just point out a few of them. Actually, only one of them, and then go to the solution Brick provides. So Haystack was one of such serious efforts that sort of had community come together, and it did a very obvious thing. What if we parse this BMS data, metadata, into different tags? So we have one tag, which then you have another tag, you have another tag, and so you sort of are doing a separation. You have some identifiers or delimiters, and you're finding these tags and tokens, something we do in parsing all the time. And then the only difference you're doing is you're giving names to those tags. So this is an ID, or this is a zone, and so on. So you have a bunch of tags now from a given metadata strings that are sort of derived automatically or semi-automatically or manually, whichever way you want to do it. Maybe there's an Excel spreadsheet in which you take the tags and then you do simple operations and you create columns of tags. Okay. The challenge, of course, is that tags have relationships. They're not just character strings. A zone belongs to a space, and equipment has a control point. So how do you capture those relations? So why do you want to capture those? Because you want to be able to reason with them. You want to be able to query them. And so this is where we put a working group of people together about, say, 5-6 years ago at Berkeley, UCSD, CMU, UCLA, and IBM and others. And we said, let's do a more systematic graph model. A graph model is one in which you have objects and relationships. We just have to define the objects and relationships in a way in which they're useful and they can be used in a programming environment. And that basically led to a brick schema that I'm going to take next 10 minutes to walk through with examples. So you have tags, which you have seen before. These are tags that refer to zones, temperature, and sensors, let's say. They represent some meaningful object or action. You could also have compound tags or tag sets. For example, a zone, a temperature sensor, which is a combination of sensor and temperature sensor. Similarly, you have location of a room, for example, so you can define the type of a tag. You begin to see that the tags are moving from character strings to having types. And from types, they will get into programming objects. So you can then also define, just like you have types, which are predefined or inherent or native, you can also have canonical relationships. And those relationships start to define your model. So for example, you could, and that becomes a standard dictionary. So the obvious thing we did was we said, okay, let's take 3 types of things: equipment, control point, and location, and create each one of them as a class hierarchy. So equipment can be of a subtype of fire safety, it can be subtype of HVAC, which can have a subtype of air handling unit, AHU. It could have a terminal unit. Terminal unit means the unit that is serving a zone, and that could be a variable air valve, or it could be a fan coil unit, whatever. Okay, same thing with control points. You could have a command, you can have a sensing information, you can have a sensor of one kind or the other. Location, a location could be geometric, or it could be logical, for example, a floor, a room, or a server room, or a laboratory. So that sort of builds relationships between these different objects of the same class hierarchy. So then you now have a sort of a emerging model, a graph model, if you will. So for example, here you have a in a brick schema, you have entity, which is point, which is a class, location, which is a class, and equipment, which is a class. You have seen this point, control point, equipment, and location. And then you have now a air handling unit that feeds. So you can see the relationship. Feeds means it actually is physically connected through a conduits to a variable air valve, and of course it will be connected to multiple of these, and that feeds a zone which serves as a room, and multiple rooms, for example, and a variable air valve has a part, which means it has a subcomponent, or it has a control point. Has point means control point, and so on. And these are your sensors and actuators. Okay. So now, once you define that, and there are lots of details that I'm skipping, which I think you can find them on brickschema.org. But basically, this is it sort of becomes an assembly for defining the programming the building resources. So and we also bring together the description relationships through RDF models. RDFs are very common in web descriptions as three-part specifications. So entity is a node associated with an identifier. For example, this is zone temperature, which is part of an example. So example defines the namespace. So you can have and they're related to each other as a triple. Triples are common in RDFs, and so these are the description resources over web, for example. So you have subject, predicate, object, where you can create a graph model. For example, a ZNT node 101 has a location in a room which is a part of a floor 1, and this ZNT 101 is of type temperature sensor. Room is of type room, and so on. So now you can create a graph model of the entire building, and then you can start to look for patterns through query languages. So your programming becomes a set of queries. The way we do programming in computer systems, for example, is modifying control flow through program counters in assembly. In case of a building as a platform, because you have to first do discovery of the resources and the control points, your programming is nothing but a set of declarations through a query language. Now let me just walk you through a few examples. And these are the relationship which I already mentioned to you, that we sort of brick encodes them. A common way of writing, especially in web programming, is you define a namespace, and then you define the API functions. So for example, namespace, this is coming from brick server. So for example, brick is the namespace, and then you have these classes. This is coming from RDF server. Similarly, you can have OWL, for example, ontologies, and you can have other servers that sort of connect to it. So you can create a distributed web-based computing environment. Okay. All right. So let me just now start to walk you through examples. So I told you about the namespaces I'm using, and they're using brick prefixes, but basically you have brick, which sort of refers to the brick schema. There was I think this might be deprecated, it might be a brick format schema, and then you have RDF, for example, from WC. So now you have a air handling unit that serves air through multiple VAV unit, this is called terminal unit, into a zone which might have one room or more, and So this is the air being served. This is the air being removed. So this is the supply air. This is the return air. Air handling unit might be doing some cleaning here, or recycling, or temperature control, or humidity control. And you have sensors. So for example, you may have a ZNT sensor in this particular room. So you say, okay, here's how the graph looks like. It looks complicated, but it's really nice. I'll walk you through this. You have basically a air handling unit, which is central unit, that is RDF type. An example is AH1. So this is the brick class that is being instantiated here. Similarly, you have VAV unit. You have a zone temperature sensor, and then you have relationship between them. So now, if you were to program and look for a question like, what are the temperature sensors located in a zone? This could be a simple query. So you could start to write triples. So for example, you select the sensor, which is a query, and the zone where these are the three query elements. So of the type RDF type sensor in a given temperature sensor type. So that returns to you this particular temperature sensor. What is the zone that it is located in? That returns to the zone 2150. What is the and therefore you have and the connection between them, a location in, make sure that these two points are connected together. This entire query matches this particular search. Okay. So now you're beginning to see the infrastructure come up with the brick server. It's not everything. It's the start of a much bigger programming platform that is needed. But brick gives you the first portability, first systematic way of organizing, building information system in a way in which programmed access can take place. You have sensors and actuators on top of that, and you have your typical sandwich of the operating system. Now, building operating systems have started coming up. Multiples have been built. You also need historical data. You also need resource manager. You also need cron tabs. You also need timed operations. And of course, you do need control systems so that nothing bad happens. And so a general application workflow would authenticate not only the applications, but also users, so that a user, before they can actually run an application on their cell phone, for example, or a smartphone or on your desktop, they actually get authenticated for their ability to use the services or even read data. And this security, in reality, is a little bit more complex than that. I'll just walk you through a few basic points, just so that people who are much more hardware oriented are sort of aware of that, how the security is maintained. So all your interactions are through the internet, but then of course you do have a industrial control internet, which needs to be much more secure, and therefore that particular LAN is usually we use some kind of a backnet connector to go from the internet industrial control network to the internet back and forth, so that your application is run in the open network, and then your the programs that are actually controlling building operating systems. It could be buildings in other cyber physical systems. It could be even more critical things, for example. Just to summarize, building brick applications really operate upon a graph model. And what does this graph model do? This graph model it captures the building resources, their relationships, their functional relationships, their spatial relationships, their temporal relationships into a model that can be queried through a programming interface for reading information, for writing information. So it's an interface to find relevant resource into buildings. This is fundamentally different, for example, from a typical computer system where the resource discovery is not an issue. It is already encoded into the assembly language. It does not get shown up to the application developer. So application developer does not have to worry about where the memory is or where the storage is and where the resources are. And that's where the mediation by the operating system comes in. We have created applications in 8 different types of applications, 8 different categories. One is occupancy modeling, which is important even before we got to COVID. For example, how many people are in a particular space, how long have they been there, and so on. Energy apportionment, I'll walk you through one example of that. That is, you know that this floor is consuming this much kilowatt hours, but you want to know how much of it is for heating, how much is for cooling, how much is for networking, how much it is for lighting, and so on. Web displays, model predictive control, which sort of is a real-time feedback control, participatory feedback, where the attendees might be giving feedback, or there could be feedback about comfort conditions. FDD refers to fault discovery and diagnosis, and this basically means identifying if there are faults in the system. It could be under normal conditions, for example, some part of the HVAC system is degraded, or it could be under extraordinary conditions like building needs to be evacuated, which room is occupied, which room is not occupied. NILM refers to non-intrusive load monitoring. So here monitoring without actually having equipment monitoring, that is inferring the load based on other information. And demand response, or DR, which sort of is the ability to control usage. So a query returns associated names. In your case, remember when you start talking about tags in the metadata, their locations, which is what UIDs are, and then these queries can search for control points, spatial function relationships. So of course, a building is not just so Brick Server is just a programming interface, but there needs to be some database where the building data resides. And we have been building those at UCSD with our partners in CME and others. It's called Building Depot that has a number of buildings in there. There is also other alternatives, Mortar, for example, built by Berkeley, or its earlier version, HODDB, and other. And there are also authoring tools that are appearing with respect to Brick and in operating systems. Brick now is part of a consortium, and which is where there are a number of companies. GCI, Johnson Control, is primary in that promoter of that standard. And more tools are coming up. I'm going to very briefly touch upon towards the end on metadata normalization. So you could have applications, and now I'm going to quickly go through. I'm not going to go line by line, but just tell you in higher level terms as to how an application looks like. So for example, you have hundreds of zones in a building, and you want to find out which part uses what energy, how much, and what do I change to change the energy usage. Oftentimes this requires a big simulation models like Energy Plus or others, or you can do instrumentation across the building, or you can use historical data. Now I'll show you how you can do that by just simply monitoring HVAC system. So we built a system called a soft application called HVAC meter, and what it does is it has an air handling unit, and that serves multiple VAV units. Each of those have various sensors. For example, it has sensors measuring outside air. It is also mixing air, for example, with the return air. And so it has a return air temperature sensor. It has a mixed air temperature sensor. This is called an economizer. So depending upon how you set the economizer, you can change the fraction of air that is coming from return of the building to the outside air. Of course, in infection control days, you want to minimize the return air and maximize outside air. But that takes more energy, though. Similarly, on the supply side, you have supply sensors that are going to each of these VAVs, and a VAVs looks like this, which has its own sensors, the flow sensors. So you can even start to imagine that if I'm measuring supply air temperature, and then I'm measuring the temperature being seen by each of the VAVs, I can start to get a picture as to what the heat loss is in different zones, for example. Generally speaking, you have systems, and I'll show you a picture of these where you have both hot water loops and chill water loops that sort of manage the temperature control. Generally speaking, chill water is not routed to the VAV units, partly because of facilities reasons. Chill water usually causes condensation that can cause water leakage, and therefore cause mold and other things. So normally we don't circulate the chilled water to local domains. So you can then write up the equations that sort of measure the temperature, measure the airflow, and then based on that compute how much energy is being extracted or inserted into a given zone, and then you add them up as a total energy usage. And the energy usage could be because of the change in water temperature versus change in the air temperature. I know I see some questions about questions. So Ricardo, please do feel free to interrupt me and ask questions if necessary, if there's any clarification I can do. So program is nothing but finding the building level water usage, finding the AHU points, finding corresponding VAV points. Remember, you're writing a program for that can go from one building to the other. So each of these needs to be discovered for other buildings as well. And so when you do that, your query could be find all the returns of the temperature of the return supply and mixed air temperature. So this is AHU. You look at the temperature sensors of that kind, and you this is the relationship you're looking for, all the temperature sensors, and that leads to a query of this kind, which is you're looking for a return air temperature and you want to return it for a given particular AHU. So this is the particular AHU for which you're selecting the return air temperatures. Okay. Similarly, you find the energy meters for chilled water supply and how that is changing. So that again, very analogous to that. Then you find all the control points that are controlled by a given AHU via the VAVs. So this is, you have an AHU that supplies multiple VAVs, which each of which has its own control points. So you feed that, you get that information. And then, and this of course is the feeds relationship here. And so now you have a full query. This is sort of a schematic of a query. There are a few more lines here and there, but really that sort of gives you an estimate. So we implemented that. We measured we actually measured the actual cooling power and heating power used by the building and the estimated from the airflow. And when we do that, this is the summary of that. We sort of say, okay, what is the root mean square error of 3 different buildings? Remember, this is where the discovery from buildings comes in. And how do I compare it? And if I compare it to, let's say, where I just use the mean value as an estimate. And you can see there's a significant improvement in the error simply because of the actually taking the airflow and measuring that. But even more interesting, even much more interesting, was the ability to discover that, look, the airflow is showing me this much air going in, but the VAV is giving me a different number, and it is not adding up. It is not adding up because there is a fault. There is a damper that is stuck, open or closed. So we started discovering faults into the system automatically. And in fact, when we wrote a program, so there are something like 250 rooms in this particular building. If you look at those rooms, if you were to go each room by room, you have to go up the false ceiling and look for it and see if the damper is stuck. On the other hand, if you write a program and you set up, for example, you said this is the target set point, this is the CFM. For example, this particular room, 1520 cubic feet per minute. But when we actually set it to maximum, we only get 66% of the maximum. That means the valve is getting stuck. So we identified rooms where such valves are stuck. Now, in those days, it was just an issue of saving energy. But in the days of COVID, you can imagine what problem this can lead to. You think you're getting fresh air, but your valve, airflow valve is stuck, and therefore you're actually getting a much more stale air, and that can lead to super spreading event, especially if you're in a meeting room or a conference room. So we are actually fixing those up in this particular building already currently. You can imagine the 237 zones, 250 rooms, and so on. So that's it. And if you go inside the building, I want to actually walk you through this a little bit and bring you back to the infection control. If you go inside this building, you will see, this is my office actually, you will see an air feed. So this is where the supply air comes in. And then the return air goes through this common plenum. here. So this supplies the air. This is the return air, and if you go inside it, so this is the actual schematic. You will see that this VAV, particular VAV, serves 2 rooms. So this is my office. This is my next door neighbor, Diana Rosing, I think. So no, it's the other side of the room. And so these are this is one VAV, and these are the return air. So this is the feed supply, and this is the return air. This is how the VAV valve looks like. And this damper here really is controlled by these gears, which are plastic gears you see in an RC plane. So over time, they basically break down and so on. Now, if you look at the spec sheets, this is a different room, but you can see nominal is 45 CFM, maximum 150 for this particular room. So if you look at the entire air handling system for the entire building, you basically have now big fans that are sort of supplying air to the building, taking the return air, and then relieving that air to the outside, taking the outside air, and then there is some recirculation that happens here. Okay, so this is for the entire building. Now, this is the schematic diagram. This is how it looks like in reality. This is on the roof, for example. So this is a typical air handler where you have air entering either from outside, which is this, or from the recirculation, and these are the filters here, and that is supplying to the various to the air handling units to the various zones. Okay. This is another one. This is actually at a hospital where we actually have COVID patients. So this is the return air here. This is the chilled water loop here. This is the cold. This is the hot water loop here. There are filters here, and then your supply goes in there. So you have 2 supply vents coming here, one going inside the building. Now you can see the challenge you run into. Your air is coming in, and that air has to be purified in this air handling system. You can monitor it here. You can see how good quality it is, and of course you can manage it against energy consumption and so on. This is my postdoc and students actually taking samples of the air for presence of the virus and from exhaust, and unfortunately we find quite a bit of air in virus in the exhaust. So we asked the question: can you write a program that automatically goes through the entire handling system of the building? Doesn't matter how many floors it is, and hundreds of rooms, even thousands of rooms, and automatically identifies what the set point is, what the set point should be, and how much error and this is basically what this brick program looks like. That sort of does the set point detection of the stuck-up valves. But it goes more than that. It also says, well, for this period to this period, let's say every 2-hour interval, before we meet, can I increase the air handling and then bring it back down? And how much can I increase it? So it turns out that just for a classroom, we can go from 5 air changes to 20 air changes, over 20 air changes. Now you can imagine that sort of brings the risk down almost to less than 1%. And so you can do a zone level air control when people meet to reduce the energy, to reduce the infection control, and also at the same time, because you're recycling it, you're also keeping in energy, keeping energy minimization, energy uses also to optimum. So this brick ecosystem, this emerging brick ecosystem consists of multiple tools, some of which are developed by us and our group, and then some others are developed by our partners in other schools and so on that are already available. The last thing I will say on this one, before sort of bringing our methods together, is that we're still at the early stage of this platform. Think of it like having just invented the assembly language for this computer. We still are building up the compilers and analyzers and so on. For example, metadata is still quite a bit of a pain to handle. Even when you take the metadata and structure it, you need to find ways in which you can go from metadata of one building to another building to another building. This is where we are applying quite a bit of text analysis and machine learning to automate that process. Just to give you an idea, when we see a metadata, and parsing it to different classes is what makes it structured. To do this restructuring is similar to for example, what we do in compilers. We have multiple stages. I will just give you this slide to sort of give you an idea as to how we are building this. You take the raw metadata, extract the features from it, inference from those features, what these features mean, and then you put them into the actual translated normalized metadata. And that is a set of tools. It's called Plaster that my student has built. Let me let me pull all my thoughts together and sort of lay it out to you where we are with respect to this platform. And again, building is an example of a cyber physical system platform. You can imagine transportation system, you can imagine energy grid system, you can imagine parking system. They can similarly be create into a programmable platform. And we're not talking about becoming a programmable platform by inserting or placing a computer inside a building. What we're talking about is the building resources that sort of are similar to what in abstraction what we see in computing resources, except that when we talk about data in buildings, we're actually talking about time series data. Now, the current infrastructure of cloud computing and IoT sensing allows us to create longitudinal time scale data. Rather than measuring energy consumption or at a given point in time, you can actually have a time series of energy consumption. Measuring it rather than measuring temperature at a given point in time, you can have a time series. So it sort of gives you a longitudinal view of the system operation. So this new class of applications will deploy new methods for discovering sources and their capabilities. To do all of this, we need ability to write, specify behaviors that operate over geographical distances or distributed environment, and they're not a singular computer. This concept was developed in sensor networks as macro programming, where you think of the entire network of sensors and actuators as one single unit rather than programming each one of them individually. And they are now beginning to be redeployed and reimagined in case of these platforms. You also need autonomous discovery, registration, update of devices as they're discovered even in runtime. You also need new capabilities for new inferences, determining cause and effect relationships between what building systems do versus what humans observe and experience. What we're finding is that all the logic that we did in infection control, in air handling, in energy usage is beginning to cross from higher level programming to lower level logic of the infrastructure. For example, the metadata models, the type checks that can be done on the metadata models themselves. A pretty active ecosystem of community is emerging. So this is definitely something that in coming years would be exciting things to watch. With that, I am a little bit over in time, but hopefully I've had a chance to lay out the vision for what we see as emerging programmable human spaces. And I very much thank you for your attention.
So thank you very much, Raja, for this very nice, inspiring talk. So we are open for questions now. So if you have any questions, please do it as soon as possible here using the chat channel. But I have already one question.
Yes.
So in all these very nice new smart buildings and smart spaces, I would like to see your comments about opportunities for the IC design companies and also EDA.
Yeah, so it's a very good question. Almost all IC design has been built around are on on a logical model with the interface to the upper layers of the system through memory system. Now memory and storage are beginning to cross paths and they're beginning to be unified. That's great. Non-volatility is becoming important. That's great. But when you come to the new systems, the sensing becomes a big part of your environment. And I think we are at the early stages are beginning to see indirect sensing. In other words, we know what a air sensor looks like. We know what a airflow sensor looks like in physical systems. But now, because the non-intrusive monitorings are becoming much more common, inferencing is beginning to happen. So you will start to see new class of hybrid ICs with programming with them that sort of act like new sensors. Let me just give you one trivial example. It wasn't that long ago we had resistive and capacitive touch sensors, and they were there for some time in touch screens and so on, until multi-touch started coming in, and then there's a whole software layer evolved that sort of made the IC and the human experience meld together, and now we take it for granted in how sophisticated the touch interface is. Similarly, there will be gestural systems. There will be other interfaces that are supported by some significant, non-trivial piece of hardware that could be in sensing, that could be in processing, that could be in machine learning, that could be in storage navigation. And I think that is this sort of the starting space where the new things will come in.
Okay, thank you. So if you have any question, I have a last call for questions. And so one point that I would like to also to comment with you is that we see nowadays that the number of transistors that are being fabricated in the world is exploding year per year. No, if you see the data from 2017, it's 1 sextillion transistors, 3 times more than in 2014. And then we observe that it's becoming more and more important to optimize solutions, and the optimization means to do the design of dedicated chips. No, so how you see this opportunity of doing dedicated chips to cope with all these demands on smart spaces? And
so we are very familiar, Ricardo. I'm sure you know about Makimoto waves. We go through the period of customization and standardization and then customization back in general purpose. The most immediate impact will be the number of sockets, and the sockets have been increasing lately. And I mean sockets in a metaphorical way. There's of course chip scale integration and so on, and so you're beginning to see pick up any platform. Cell phone is a good example. You are seeing a abundance of co-processing for different functions and so on, specialization of functions. That I think is a trend that will continue before the Makimoto wave of standardization hits again. The cycle will be longer. And the reason is for very simple. The heterogeneity of the functions is just significant. And so it is no longer just a question of ASIC versus a PGA type of a back and forth, but it is really, does it even make sense to use an electromagnetic inference sensor and not use some other sensor altogether or infer it from some other information? So you would find sensors being eliminated in presence of software and vice versa. And so you will have a new dimension of not custom and programmable, but physics-based or chemistry-based versus software, and then back and forth. And I think that will lead to a different cycle of virtuous new products. But there is no question that the number of stars will increase, number of sockets will street, the aggregation that happened into the star IP will now start to disaggregate again.
Okay, so thank you very much, so Rajesh, for this very nice and inspiring talk. So if for the ones that lose the opportunity to attend this talk in real time today. It was recorded and will be available in the YouTube channel in a few weeks back. And I would like also to invite all you to come back next week to attend the next CASS talk that will be done by Rodrigo Calderon Rico from Apple, California, talking about missing hardware functions to apply intelligent in communication systems. And this talk is being organized together between IEEE CASS Rio Grande do Sul chapter and the IEEE CASS Guadalajara chapter, also always in cooperation with Federal University of Rio Grande do Sul at Porto Alegre. So thank you very much to all attendees for this talk today. And thank you very much, Rajesh, to accept our invitation and to provide us with this very, very nice and inspiring talk. So thank you.
Ricardo.